everyone. Myself, Dr. Ranjith Kumar Gatla, working as an Associate Professor in the Department of Electrical and Electronics Engineering at Institute of Aeronautical Engineering. So, in today's class, we are going to discuss about some basics about the single phase AC circuits. So, which means in today's class, we are going to discuss what are the various single phase AC circuits. Of course, before we have studied about the various circuits which are related to the DC excitation. So, in the DC excitation, we have already discussed about especially with respect to the resistor. So, what is the series and parallel combination? So, in this case, we are going to discuss about the circuit which is having pure resistance, then what are the properties or what is the behavior of that particular circuit, and if it is a pure inductance or pure inductor, then what is the behavior of that particular circuit. Similarly, capacitor and the combination also that we are going to discuss in this today's class. So, first let us start with the resistance connected to an AC supply. So, we have already discussed some basics about the AC supply. So, which means what is phase difference between these two circuits and how we can represent the AC current or voltage. These things we have already discussed. So, based on that particular knowledge, so here we are going to discuss, because even though how the voltage and current equations that we have already discussed, which means usually V is equal to Vm sine omega t. So, here omega is equal to 2 pi f. So, here f is the frequency of that particular waveform, right? Frequency of that particular sine waveform. So, then here this is the circuit. Let us consider here the voltage applied across this particular resistance, okay, which is equal to V is Vm sine omega t or Vm sine 2 pi ft. Then, as we know, what is the voltage and voltage we know, so which means, and we know the resistance also, then we can find the current, because we know according to the Ohm's law, V is equal to I into R. So, of course, this is an AC quantities, so we usually represent in small letters, the small v and the small I. So, from this here, I is equal to V by R. So, we know already what is V. V is equal to Vm sine 2 pi ft by R. Okay. So, then we can substitute this Vm by R, which is equal to Im. Okay. So, this is Vm is equal to the maximum voltage and Im is the maximum current. Okay. And we know already what is maximum voltage, what is maximum current. These things also we have discussed in the previous classes. So, I is equal to Im sine omega t or Im sine 2 phi ft, right? And in case of pure resistance, okay, if the circuit having the pure resistance, then the behavior of the voltage and current is also very important here. So, because here there is a concept of phase. So, here when the circuit having the pure resistance, then here the voltage and currents are in phase, which means, as you can see here, of course the magnitude may be different, but the phase difference between the voltage and current is 0, right? So, let us consider here phi. So, then phi is equal to 0, right? So, which means here the power factor is 1. So, power factor is nothing but cos phi, which is power factor, which is equal. So, here cos 0, which is equal to 1, right? So, this is the behavior of the what is that AC circuit which is having the pure resistance. Then coming to the next case, which is a pure inductor. If a AC circuit having a pure inductor, then what is the behavior of that particular circuit? Which means what is the voltage, what is the current, okay, and what is here there is a concept of what is that, the inductive reactance also, okay, simply not the inductor, okay, inductive reactance also. Here the topic will comes into the picture. Then here similarly that we have applied a AC voltage across the pure inductor, that voltage is equal to V is equal to Vm sine 2 pi ft, right? So, then let us consider I is the instantaneous current here, but here as we know already, the voltage across this particular resistor, the voltage across this particular inductor, okay. So, let us consider, of course, here, because this is also connected across this, then here V is equal to L into di by dt, right? But we know that V is equal to Vm sine 2 phi f of t, that we know. So, from this here, if you substitute, if you can get I is equal to I is equal to minus Vm by 2 pi L into cos 2 phi ft. Okay, so I will let you know why here it is minus. Okay, that is depends on whether it is depends on the phase difference, leading and lagging, right? So because here I is lagging behind the V, okay, by 90 degrees, so that's why here we will put a minus sign. So here then from this equation we can write I is equal to minus Vm by 2 pi L, of course, because here it is usually in the same case, in the previous case it was Vm by R, but here it is Vm by XL. Okay, so which means here this means here it is XL. So XL, which is the inductive reactance, which is equal to 2 pi F into L, right? So that is what here. Then I is equal to minus Vm by 2 pi Fl into cos 2 pi Ft, right? Then I is equal to, I mean, if you simplify this, because just in the place of 2 pi F, here we have substituted the omega. So here minus Vm by omega L into cos omega t. Okay, so which means here Im is equal to, we can substitute this particular term as a Im. Okay, so Im is equal to minus Vm by omega L, right? So which means here we can write it as a I is equal to then Im into we can write this cos omega t in terms of sin omega t minus pi by 2. Okay, cos omega t minus pi by 2. Then here substitute this one Vm by omega L as a Im, so that this equation will become here I is equal to Im sin omega t minus pi by 2. So which means here before in case of resistance we got I is equal to Im sin omega t only. Okay, because the phase difference, actually the general what is that notation here, it is equal I is equal to Im sin omega t plus phi. Okay, so in case of resistor this phi is equal to 0, so that's why we didn't consider, so that we got I is equal to also Im sin omega t. Okay, but in case of inductor here I is equal to Im sin omega t minus pi by 2. So here which means here phi is equal to minus pi by 2. Okay, so here plus and minus is depends on whether it is a leading or lagging, right? So which means here, as you can see here, this here it is started from here. Okay, so but the current is lagging behind the voltage by 5 by 2. Lagging behind the voltage by 5 by 2. So which means here the current lags the voltage by 90 degrees. The current lags the voltage by 90 degrees. Right? So that is what here, because of this here we got the minus 5 by 2. So which means here, if you include the J operator, okay, so then I is equal to minus J by omega L into V. Okay, so that's what here. Then that's what as I mentioned here, the inductive reactance, which means here XL is equal to 2 pi Fm. So we can write I is equal to, or in other words, okay, so V by J XL. Or if you just what is that multiply the numerator and denominator by J, then you will get here minus J into V by XL. So this is the behavior of the current, okay, in case of the when an AC supply is having or connected across the pure inductor, right? Then coming to the capacitor connected to the AC supply, right? The capacitor connected to the AC supply. So we know already here this equation, the current I is equal to C into dV by dt. Okay, so before it was L into di by dt, V is equal to, and here I is equal to C into dV by dt. So here we know already what is V, because V is equal to, in this case also let us consider Vm sin 2 pi ft. Okay, so then here V is equal to Vm sin omega t, then I is equal to C into, you just substitute wherever the V is there and apply the differentiation, then you will get I is equal to 2 pi fc Vm cos 2 pi f t. So we can replace here the 2 pi ft as a omega, then this equation will become I is equal to omega c Vm cos omega t. Okay, so this one we can write it as a omega c into Vm Im, because this just forget, I mean just put alone this cos omega t. So this term we can make it as a because we know already the standard form of this particular equation, I is equal to Im sine omega t plus phi. So we have to convert this particular equation into this particular form. So that's why here we just replace this omega c Vm as a Im. Then I is equal to here Im, and this cos omega t we can write it as a sine omega t plus phi by 2. So that's why here sine omega t plus phi by 2. So which means here the phi, okay, that means the phase angle between the voltage and current, here it is phi by 2. So this is plus phi by 2. So which means it is leading, okay, the current is leading the voltage by 90 degrees, which means here if you make it like this, then this current, this is phi by 2. So the current is leading the voltage by 90 degrees. Or the same thing we can write in, we can say in another words, the voltage lags 90 degrees beyond the current. Okay, so this way also we can make the statement, right? But anyway, here we are considering the voltage as a reference, so that's why we should take the reference as a voltage, and based on the voltage reference, then we can estimate the phase, whether it is a lagging or leading. So that's why here the current leads the voltage by 90 degrees. So that is what we have to say the statement, right? Then of course, if you want to find the RMS current, then I is equal to here omega c into V. Of course, we know that what is omega. Omega is equal to 2 pi f, right? Here there is a concept of again the capacitive reactance also. Before in the inductor, we were having the inductive reactance, but here we are having the capacitive reactance. So the capacitive reactance here Xc is equal to 1 by 2 pi Fc. This 2 pi f we can make it as a omega, so that we can write this one as a 1 by omega c, right? So simply here we can also write this one I is equal to plus j into v by xc, or if you can multiply and divide the j with the numerator and denominator of this particular equation, then you will get here minus v by j xc. Okay, so this is how we can find the current equation in case of when the capacitor or the pure capacitor is connected across the AC voltage source, right? So now we can conclude based on these three cases. So in the first case, when there is a pure resistor, okay, is connected across the AC voltage, okay, or connected across the AC supply, then the phase difference between the voltage and current is 0, right? And because the voltage and currents are in the same phase, are in phase, so that the power factor is 1. Like that, we can conclude. And in the second case, when there is a inductor connected to an AC supply, then the phase difference between the voltage and current is 90 degrees. Of course, in capacitor is also 90 degrees, but leading and lagging is the difference, right? So in case of inductance, there is another concept is called the inductive reactance instead of just inductance. So there is a concept of inductive reactance. So inductive reactance we usually represented as a XL. So that XL is equal to 2 pi f into L, or simply we can write it as a omega L. So omega is equal to 2 pi f. Then there the current, the phase difference between the voltage and current is 90 degrees, and we can say in another words, the current lags behind the voltage by 90 degrees. So that's why there the current equation I is equal to Im sine omega t minus pi by 2. Okay, so here the minus sign indicates the lagging. If it is a plus sign, then it is a leading. So that is the concept in case of when the inductor is connected to an AC supply. Then coming to the capacitance, okay, or the capacitor is connected to an AC supply, then in this case, of course, here also the phase difference is 90 degrees, but here the equation of the current I is equal to Im sine omega t plus pi by 2. So here plus means it is leading. So the current leading the voltage by 90 degrees, right? So when coming to the phase angle, in both the cases, it is 90 degrees same. But when coming to the leading and lagging concept, in the case of inductance, the current is lags behind the voltage by 90 degrees, and in case of capacitance, the current leads 90 degrees, leads by 90 degrees, leads 90 degrees by the voltage. So this is, and here, same like in the inductance. So here in the capacitance, there is a concept of capacitive reactance or the capacitance reactance. So this can be represented as a XC. So this XC is equal to 1 by 2 pi F into C, right? Or in another words, 1 by omega C. That is the capacitive reactance. Then this is the phasor representation, right? This is also very important. Then coming to the next concept, okay. Suppose if both resistor and inductor are connected in parallel, then what is the behavior of the current? Right? What is the behavior of the current? So that we will see in this. So here, first of all, what is the voltage across, the total voltage across these particular two terminals? These two terminals are across the load. Let us consider the load is a combination of resistor and inductance. So here we can make it as a, here it is VR and here it is VL. So we know already what is VR and what is VL. So here VR is equal to I into R and VL is equal to I into L J XL. Right. So now we need to find these R value and XL value so that you can find then R, if you just simply add, because here this is an AC, so we should not add simple arithmetic. Okay, we have to what is that the vector addition that we have to perform. So which means here the total voltage V, which means across these two terminals, across the load terminals, V is equal to, so I into R plus J into XL. So from this we can find here I is equal to V by R plus J XL. And we know what is XL. So here XL is equal to omega L, or in another words 2 pi F into L. Right. Then actually what this we can make it as a, this is a impedance of that particular load, or the load impedance we can make it as. Of course, in simple words we can make it as a Z, or sometimes they usually represent it as a Z suffix L, which means the load impedance. So the load impedance is equal to R plus JXL. Right. So if you want to simplify this furthermore, just here I am trying to multiply these R minus J omega L to the numerator and denominator. So that here this equation will become I is equal to V by R plus J omega L into R minus J omega L by R minus J omega L. Right. So then this one will become, here as you can see, this one we can make it as a, where here it is, yeah, this one. Okay. So this one we can make it as a plus B minus A minus B, A plus B into A minus B, so that A square minus B square. So we can just simplify this so that the I will become V into R, because we are just writing the real terms at one place and the imaginary terms at one place. So here the real term, here it is VR by R square plus omega square L square, and here the imaginary term is minus J into V into omega L by R square plus omega square L square. So here, which means here, of course here you may get the doubt here, why minus J, okay, R minus J omega L, because here R minus, here it means, okay, the same like in the minus 5, okay, here minus means, minus J indicates that the current lacks the voltage, because here the inductor is there. So the nature of the inductive load here it is, the current lacks the voltage by certain, of course if it is a pure then 90 degrees, okay, but here it is not the pure inductance, it is a series combination of inductance and as well as the resistance. So that's why we can't say it is 90 degrees, but just we can say, but still it is a, still the current lacks the voltage only. This is in the complex form and this is in the Cartesian form. Okay, both the forms that we have written, right? So of course that we can write into the polar form also, because as you know this is the rectangular form. Okay, so then in the polar form, then I is equal to V by square root of R square plus omega, because you know already that is R at an angle of theta, right? That is the polar form. So R is equal to, as you know, square root of R square plus L square. Okay, so that is different issue. Then R at an angle of theta degree. So then I is equal to V by square root of R square plus omega square L square at an angle of phi L. Then what is phi L? Here it is R phi L, which is equal to tan inverse omega L by R. right? So here minus 5 indicates again the lagging, because the negative sign of that particular degree indicates the lagging. Okay, so which means here this is, let us consider here it is VL, okay, and here it is VR. Then the resultant between this VL and VR is the total voltage V. Okay, then the total voltage V is lags the current by an angle of phi L, an angle of phi L. So this is the current I, right? Because in case of VR and IR, the current and voltage are in phase. So that's why here this is the V and this is the I. Both are in the phase, same phase. But in case of VL and I, okay, this is lags behind the voltage by 90 degrees. So that's why here it is total, it was 90 degrees. Okay, but this is the resultant vector of V, which means the total V is equal to the vector addition of VL. Of course, let us consider VL plus VR. Okay, so then now the difference between the current and the voltage, here it is this angle. So this angle is the phi L. Okay, but still, as you can see, the current is lags behind the voltage by an phi L, not 90 degrees. So that is what you have to understand. So then here the I is equal to V by square root of R square plus omega L square, that we know. And here there is a concept of power factor also. The power factor is nothing but cos phi L. Okay, so here the phi L are, I mean, simply the standard notation is cos theta. So theta is the angle between the voltage and what is that? The current, right? Simply the complex impedance also, here Z is equal to square root of R square plus omega square L square. So this is about the RL. Similarly, here you will get the RC also. So RC is leads. That is the only difference. Okay. So similarly, you know, here also the total voltage V is equal to the vector addition of the voltage across the capacitor and resistor, and as you know already, VR is equal to I into R and VC is equal to I into minus JXC. So you just substitute, then you will get this equation. Okay, so from this you can find the I value also. I is equal to V by R plus R minus JXC. So you know already what is XC. You just substitute here XC, then you will get, then you can get the final I equation. And in the complex form, Z is equal to R minus J by omega C. Before it was R plus JXC, but here it is R minus J by omega C, or in other words R minus JXC. That is also we can write. Similarly, the same way in the previous cases. Okay, but here we will get the plus sign. The plus sign indicates the leads. Okay, so then which means again here VR and VC, because here VC is leads. Okay, here it is the current. So that here the phi angle is phi C, because before it was phi L that we are considered. Here it is the phi C that we are considering. So again here the power factor, here it is this one. So just we are converting the rectangular form into the polar form. So this is all about the basic electrical circuits or basic AC electrical circuits. So in the next class we will discuss some numerical problems based on this particular concepts. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.